I wanted to mention a few things on D2L. I had our completed class notes. They were saved as multiple pages per page. So if you've tried to reference those, you would have noticed that each page we did in class was super, super small. If you haven't noticed, that's fine. I've uploaded full page versions at this point. So whomever sent the email, thank you. Also, you may or may not have noticed in MML, when you're doing some of your homework, at the end of the number here on the left-hand side, you might notice some of them have a -T next to them. Has anybody noticed that? Okay, I don't know if I can find one, but probably not in this section. Anyhow, if you notice a -T next to this number here, it's meaning for you to use technology like a graphing utility or something like that. Since we're not able to use those on exams, those -T problems wouldn't be on the exam. It's just for, since you have access to something that can kind of help you, your exploration further, sometimes they do show up in the homework. So I wanted to make that clear as well. Has anybody thought about forming a study group at this point? Or is it too early? You have? Yeah, a couple people. So yeah, if anyone's interested in a study group, let me know and I can help facilitate that. It might be a little bit early in the semester, but really this material picks up really quickly, especially after chapter 2. Not that it's not fast already, but even more so in chapter 3, chapter 4. So I think as soon as you could get those study groups formed, the better. So let me know if you're interested. Okay. Questions on the homework? So we left off in 2.3 with this example. And again, what we're moving towards is computing limits algebraically or analytically. So not looking at a table of values, not looking at a graph, but just old-fashioned by hand. How do we compute limits is really what we want to focus on. The other stuff sort of helps us get our bearings on what a limit actually is. But this is what we want to focus on. So we have to evaluate the limit as x approaches 1 on the given function. And so hopefully we immediately see the issue with trying to evaluate that limit directly. If we plug 1 into our function here, we're dividing through by 0. Not like we saw with a rational function, just because you end up dividing by 0 initially in the function doesn't always mean you can reconcile that, right? Sometimes we can get that factor that's causing us to divide by 0 to divide away in the sense where we have a hole in the graph. Sometimes, as we'll see in 2.4, there's nothing we can do algebraically to get rid of that factor in the denominator that's causing us to divide through by 0. So the rule of thumb is kind of a trial and error thing. Oftentimes it's not obvious as to whether, for instance, in this example, that factor of x minus 1 in the bottom will go away at all. But we do need to try things. With radicals, the general method is always to use the conjugate. Did y'all look that up? The conjugate? Or do you remember what the conjugate is? Like if I had something that was a factor like a plus b, what's the conjugate?
A minus b.
Yeah, a minus b. Similarly, if I have a factor of a minus b, my conjugate is a plus b. So what's the advantage of multiplying those conjugates together?
Some values cancel.
Some values cancel, yeah, so more specifically.
You get the same denominator.
Say that again, sorry.
You get the same denominator.
Well, what do you mean, like the denominator here? This will, well, if we're gonna utilize the conjugate with a fraction, we have to multiply top and bottom by it, otherwise we're gonna change the value of the fraction. So the denominator would actually change. Just as far as this thing versus its conjugate, what would be the advantage of multiplying those things together? What does it do for us? What's a plus b times a minus b?
A squared minus b squared.
Yeah, a squared minus b squared. So when we multiply conjugates together, so this times this, what we get is a squared minus b squared. Because the cross terms add up to 0. So multiplying through by a conjugate allows us to deal with the difference of squares. That's really the advantage of involving a conjugate. We can see that's particularly of interest to us because we do have radicals involved. So when radicals are involved and we can square them, then we can get rid of the radicals. Yeah? So that's why we want to look at the conjugate of the thing involving the radicals. Because once we multiply through by the conjugate, then this thing's going to be multiplied by its conjugate, which will give us the difference of squares, and those radicals will go away. So let's look at that, how that emerges. So we're going to take this. Now you can either work with the function by itself, simplify it algebraically, and then put it into the limit, or we can just keep writing limit as we simplify algebraically. It really doesn't matter. I will say that I've noticed on exams when people are computing limits that they're not putting limit as x approaches whatever in front of their algebra. So just make sure that your notation is consistent. If you're simplifying an algebraic expression, that's fine. But the moment you start computing limits and plugging in values, you need to have the limit in front of it. So please be technical with your notation. Okay, so we have our limit here. The nature of the function, we're going to utilize its conjugate. So we're going to say, what's the conjugate of the square root of x minus 1?
Square root of x plus 1.
Square root of x plus 1. So I'm going to multiply that by the square root of x plus 1. And again, I don't want to change the value of the fraction, so I have to multiply the denominator by that as well. Otherwise, I'm totally changing the function. Let's see how much room I have. So then we just need to see what this is algebraically. So when I multiply out the top, what do I get?
X minus 1.
Do y'all agree? Multiplying the numerators together, I get x minus 1. So we already said that this is a minus b and this is a plus b. Their product is a squared minus b squared. So the square root of x squared is just x, and minus 1 squared is 1. Now this is always going to be the case. When you have some factor in the denominator causing you to divide through by 0, you want to leave it as it is. So this is the issue right here, this factor of x minus 1 in the bottom. At first it's tempting to multiply that through. Since we did that with the numerator, why not multiply all of this through by the denominator? Anybody know why we wouldn't do that? Why wouldn't we multiply the denominator out?
Because you can cancel the x minus 1.
Yes, because the issue was dividing by 0 from this factor of x minus 1. If we multiplied all of this out, we're losing that piece of information. It's getting scrambled in with all of our multiplication. So we want to explicitly leave what's causing us to divide by 0. We want to leave that alone. Don't ever multiply that through other things. Because correct, we do see now that this factor up top and this factor in the bottom will divide away. So we know our function is algebraically equivalent to 1 over the square root of x plus 1. And we are still computing the limit as x approaches 1. Are there any questions on what we've done? So we can evaluate this limit directly now. What is this limit equal to?
1/2?
Yeah, 1/2 or 1/2. So based on our discussion last time, the function root x minus 1 over x minus 1, what happens on that function? What is our work showing us is going on there? Yeah, we have a hole. This function has a hole. We were approaching a finite number. X is approaching a finite number, and the y values are also approaching a finite number. The original function was undefined at this value we're approaching. So 1 isn't in the domain of this function, but we get an actual value according to the limit in return. So we have a hole on that function at 1/2. We'll look at the graph in a minute. So let's just write that out. There's a hole on this function at 1/2. X is approaching 1, y is approaching 1/2. And we'll look at another example where this is where we have to use the conjugate. So you don't always have to use the conjugate. It's just think of it as the most general approach to limits involving radicals that you can't initially evaluate. Everybody good on that?
That's supposed to be x minus 1 and 2.
Oh, x minus 1, yeah. Yeah, sorry, I wrote that down wrong. Thank you. The second method, it's not always applicable, but when it works, it is much more efficient. So this time I'm just going to start with the function, simplify it algebraically, and then compute the limit. Remember, it doesn't matter if you're carrying the limit through all of your algebraic work, or if you're doing the algebraic work first and then computing the limit. But again, whenever you compute the limit, make sure you're noting that by using the proper notation. We're not used to factoring things like x minus 1, for instance, as a difference of squares, or looking at that as a difference of squares. But when we can recognize the pattern, this, like I said, this method is much more efficient. So if I think of x minus 1 as a multiplied out version of the difference of two squares, if I think of it like this right here, then maybe I can rewrite this as a plus b times a minus b. In other words, if I think of this as a squared, and this is b squared, then I can sort of reverse engineer that, right, according to a plus b times a minus b. So if a squared is x, that means a is square root of x. If b squared is 1, that means b is 1. So we have a minus b times a plus b. So y'all agree that's how I can factor x minus 1 in that manner? We're not really used to looking at that. When we factor difference of squares, it's always like, you know, x squared minus 25 or x squared minus 100, right? But we can factor like x minus 1 or x plus 3 as the difference of squares. So once we see that as how it's factored, notice we're in the same place we were just a minute ago, because that function simplifies now to 1 over the square root of x plus 1. So then I know computing the limit on this is equivalent to the limit on this. So therefore, the limit as x approaches 1 on the simplified version of our function does yield the same result. If that's weird, then just disregard. You can always default back to the conjugate. So here's a graph of our function. As you know, we discussed this last time. Graphing utilities aren't always accurate, especially when it comes to showing a deleted point or a hole. But our work shows us that as we approach as x approaches 1, this function approaches this y value, which was a half. Are you all right with that? Does that make sense? Any questions? Yeah.
So there's a hole in the second one at square root of x minus 1, I guess?
Well,
Is that different than the first one?
no, we started off with the same function. Instead of multiplying the conjugate to simplify it, we just chose to factor the denominator this time to simplify it. But it is the same function, right? Limit as x approaches 1 on this was a half, and that's the same as what we started here. Limit as x approaches 1 on this is equal to all of this, which is a half.
Okay. And the hole's at the same spot?
Same spot, right? Because x is approaching 1, y is approaching 1/2.
Oh, okay, that makes sense.
Yeah. And again, if your function's defined, if this function were defined at 1 and we're approaching 1/2, then there's no longer a hole. It's just due to the fact that our original function wasn't defined at the value we're approaching that we have a hole. Any other questions? Just to look at a few of these, if we started off with like x minus 2, how could we factor that? In the same line we were factoring above.
Root x plus root 2 times root x minus root 2.
Yeah, right. We could factor this as root x minus root 2 times root x plus root 2. And so on, we could go. If we had x minus 3, then we could factor that as root x minus root 3 times root x plus root 3. So in general, x minus a, root x minus root a, times root x plus root a. Again, that method does not always work, but if and when you can notice that pattern, it will be a little bit more efficient. Questions?
Can you give us an example where it wouldn't work?
So an example where it wouldn't work is on the next page, the next page. So something like that, we wouldn't be able to factor. I mean, we could factor the top in this instance, like if this is a squared and this is b squared, we could factor the top. But the issue here is that we're dividing through by 0 with this factor of h. So, however we factored this right here, we're not gonna get another factor of h up top to cancel that in the bottom. So that third example there is an example of where we would need to utilize the conjugate to simplify. So we'll do that in a minute. Similar example here, the limit as x approaches 9 on our given function. First thing we see, we've got the sum and or difference of a radical expression here up top. So we could utilize the conjugate, square root of x plus 3, multiply that on the top and the bottom. Or we could recognize that we could factor this. How could we factor this? What would we focus on factoring? The denominator. So how would our denominator factor?
Square root of x plus 3 and then square root of x minus 3?
Yeah, square root of x plus 3, square root of x minus 3. Because again, we're viewing this x minus 9. That x is our a squared. The 9 is our b squared. So if a squared is x, a is root x. If b squared is 9, b is 3. So much more efficient to do that. Again, not necessary if you want to multiply through by the conjugate and try that. You'll see we end up with the same exact result. So that allows us to cancel the factor that was causing us to divide by 0. And we're no longer dividing through by 0. We can evaluate that limit directly. As x approaches 9, what's our limit? 1 over 6. So here's a part of that function. What do we know about the function? The graph of the function anyways?
There's a whole,
There's a hole, where at?
116.
1/6 for the y value?
916.
Right, good. So x is approaching 9, the function's not defined at 9. So there's a hole on that graph. At 9/1/6. So that's our,
Will always be the limit value?
well, sorry?
Will the x value always be the limit?
Yeah, so if you've got a hole, you can always compute a limit and it'll always be a singular value, right? Just think if we approached an actual point on the graph, if you approach an actual point, there's one and only one output for that function there. It's the same with the hole, it's just that point we've picked out, it's been deleted. Is that what you were asking?
No,
No.
but I think I answered my own question.
Okay, well, what were you asking?
Like when you're doing the ordered pair, if it's x approaches 9 or x approaches 1, is x value always 9 or 1? On your ordered pair.
Yeah. So like we're approaching 9 here, so the x value was 9. The last example, x was approaching 1, so that x value was 1 for the whole.
Thank you.
Yeah, somewhere we actually wrote that down. It was very generic how we wrote it down, but we did have that somewhere. I don't remember if it was in 2.3 or 2.2. Just so you can reference. Maybe it was in 2.2. It was in 2.2 where we wrote that down. No, it's here. So this page, remember we said that if you've got a function that's undefined at x equal to a, where a is a finite number, but we are able to compute a finite limit. Here's the limit value, n or l, whatever you want to call it. then the whole's always at a comma n. So x approaches a, the limit is equal to n. Do y'all have any other questions? So all of it seems kind of technical, but honestly, it's nothing you haven't done before. We haven't associated limits to prior algebraic work. That's really the only modification we're putting in here. So hopefully all this algebra seems familiar to you. I really think that 80% of this class is algebraic stuff. 20% of this stuff is formulas for calculus, and then the rest of it's like simplifying and solving equations and stuff. All right, so example 3. The issue here again with evaluating this limit is we're dividing by h, and h is approaching 0. So it's causing us to divide through by 0. So then our goal is to algebraically manipulate this function so that we can get a factor of h on the top so that it will cancel with this factor of h on the bottom. So we did already allude to our method here. We're going to multiply by the conjugate of the numerator. And we're going to do that to the top and bottom. So the problem was the h in the denominator. We don't want to multiply that through, so we're going to leave the denominator as it is. The numerator we're going to multiply out. So when we multiply the numerator out, what do we get?
Plus h minus 196.
Okay. (196) plus h minus 196. Do y'all agree? So the top is a minus b times a plus b. So we know that turns into a squared. If we square the square root of 196 plus h, we just get 196 plus h minus 14 squared, which is 196. So this here is our a squared minus our b squared. If you multiply those out by making, the grid, or if you have to write out FOIL, or whatever you do to multiply those out, I don't think there's a right or wrong way to do that. So however you do it, just do it that way. So we should get 196 plus h minus 196. Again, we're going to leave the bottom alone because we're hoping to get rid of this factor here. When we combine like terms in the numerator, we're just left with h in the numerator. So we have the limit as h approaches 0, h up top, h down below. And so that's what's going to cancel that division by 0 for us, and allow us to actually compute this limit. Do y'all have any questions on that?
for the conjugate, if you didn't have the minus 14, if you just had square root 196 plus h, is there like, can you do that as a conjugate? Would you do 196 minus h under square root? Like if you just didn't have the negative.
Oh, no, at that, if it were just this, at that point, maybe we would try just multiplying it by itself. Because when we multiply root by root, it goes away, right?
Okay.
Like square root of 2 times square root of 2 is just 2.
Okay.
But, something like that, you wouldn't see anything like that, because there's no way to simplify that.
Okay.
In other words, you would still end up dividing through by h. We'll see that instance in the next section.
Okay.
But nothing that elaborate.
Okay. Substitute pH for 0.
Right. So once we've simplified, now we can compute this limit because we're no longer dividing by 0. So what is that limit equal to?
1 over 28.
1 over 28, right? Because as h approaches 0, this is 1 over square root of 196 plus 0 plus 14. So we have 1 over 14 plus 14. Do we have a hole in that graph at 0, 128? 128? Is there a hole there, or is it a point? Yeah, how do we know it's a hole?
Because it's a finite limit.
It's a finite limit, yep. And more importantly,
You have to cancel something.
we have to cancel something. The original function's not defined at 0. Typically, we see functions of x, but these example 3 and 4 do illustrate something that we've seen before prior to this course. Questions on this example? Okay, so functions that deal or that have radicals involved, we've seen a couple of ways to handle those. How about functions that involve complex fractions? What's our algebraic method? Just ignore that limit. What's the algebraic method to simplify a function like that?
Multiply by 1 over 8.
Okay, like terms, meaning,
So multiply 8 over 9 plus h times 9 over 9 minus 8 nines times 9 plus h over 9 plus h. And that the denominators of the top get the same denominator.
okay,
So you can subtract those and get them together.
right. Sorry, what did you say? What was your?
I was saying you just multiply by 1 over h and then look at it. Just because
Okay.
I hate looking at lots of fractions.
All right, yeah. So we hate looking at multiple fractions. So this one suggestion was to get rid of the denominator 9 plus h and this 9. So how do we get rid of these denominators? So that we just have something up top and something down below, not multiple fractions. The other suggestion was multiply by 1 over h, 1 over h. So I just want to show you, if we multiply both top and bottom by h, or sorry, 1 over h rather, we've got to remember to do that to both of these. That's really not going to eliminate the problem for us, because true, the denominator is 1, but now this becomes 8 over h times 9 plus h minus 8 over 9h, and we're computing still the limit as h goes to 0. So now it's, whereas it was in just one occurrence here, now we have 2 occurrences of it. It's not that it's wrong, but it didn't help us. That's algebraically sound, but it didn't help out. Okay, the other suggestion was clearing these smaller fractions denominators out. You can also take what you have in the numerator, add those together, because or subtract those together rather, because in order to subtract these two things up top together, we have to have a common denominator. It's honestly just easier to eliminate the denominator from the inception instead of carrying that through the process. But either method will work. If you want to subtract these two fractions up top first and then handle the division by h, feel free to do that. It's a little bit lengthier of a process, but it's still algebraically valid. Well, to clear these fractions, we're just going to involve the lowest common denominator. The lowest common denominator of these two that we're trying to clear. We're ignoring the division by h at this point. A lot of times some of these problems could be a little more complex, and you know, I always thought finding the lowest common denominator was super tedious. So instead of racking your brain trying to find the lowest common denominator, what you can do is just take any common denominator and multiply through by that. Will always clear the fraction. Then you have to simplify. The only advantage of finding the lowest common denominator in situations like this is because once we multiply through, there is no simplification that needs to be done. That's the only advantage of the lowest common denominator. But I personally think in a lot of instances, just a common denominator is easier to find because all we have to do is multiply each denominator together, right? So we wouldn't worry about if it's the lowest common. Honestly, that doesn't really matter. I think it's easier to simplify after the fact. So like, you know, if you had like 1 over x plus 1 over x squared plus 1 over x minus 1 minus 1 over x plus 1, instead of trying to think about the lowest common denominator, just take all of the denominators and multiply them together. So this is my common denominator, x times x squared times x minus 1 times x plus 1. And then I could just multiply through by all of this and simplify after. Is that clear? Makes sense? It's much easier initially just to take the denominators and multiply them together. Okay, so up top, if we multiply through by our LCD, we will eliminate both fractions. But again, if we multiply numerator by that, we have to multiply our denominator by that. So hopefully everybody remembers this process. It's been a while for some of us, but you know, that was a pretty common thing we did in whatever algebra or pre-calc. All right. Again, the h in the denominator is causing the issue, so we don't want to multiply the h through the denominator. We're going to leave the denominator as it is. What does our numerator turn into?
Negative h.
Just negative h, right?
Negative 8h.
Yeah, negative 8h. But what we're doing is we're distributing the 9 times 9 plus h to both of these. So let me just write it out. So just distribute our LCD to both terms in the numerator. And then the smaller denominators that we had up top are going to go away now. So our first term, the 9 plus h cancels out. So we've got the 9 plus h canceling with this 9 plus h. You're left with 8 times 9. Second term, we've got 8/9 times 9, 9 plus h. So the 9's divide away here. We're left with negative h, or sorry, negative 8 rather, times the quantity 9 plus h. Is that okay? Anybody have any questions? So notice, like computing this limit, we haven't even done calculus yet, right? It's all algebra at this point. There's no calculus being done. Combine like terms in the numerator. So we have our 72 distributing the negative 8 minus 72 minus 8h all over h. So we have 72 minus 72, that's gone. Gives us the limit, as h goes to 0, minus 8h over h. Does that look all right?
Can you explain what happened to the h times n times n?
Oh yeah, I totally forgot it. 9 times 9 plus h, still there. 9 times 9 plus h, still there. As you should have been.
I'm like, is everything canceling out from up
Is
top?
it up here too? With the 72 minus 8?
Yeah,
Okay.
I totally forgot that.
Okay.
Oops. Yeah, totally dropped the ball. Thank you.
Thank you.
All right, it looks better. All right, so what that's done is now we can cancel the division by 0, right? That is going away. So we can now compute this limit. H goes to 0, negative 8. Okay, so that limit would be what?
Negative 8 over 81.
Yeah, h goes to 0. This is negative 8 over 9 times 9. So negative 8 over 81. Do you have any questions on that?
So on the exams, would you prefer us to answer in fraction form, or would you like us to round to decimal form?
Thank you. Typically, you want to leave your answers exact. If it doesn't specify in the instructions, negative 8 over 81 or its decimal equivalent is either acceptable or are acceptable answers.
What happened to the 9 times h?
We're at here.
No, very last one, you have minus 8 all over 9 times 9 plus h.
Uh-huh.
So the 9 times h in that last part.
Yeah, so h is going to 0, so that thing
Oh,
is
I
just
see.
0. Yep, I'm gonna put that in. This is going to 0. Are there any other questions on that? Yeah.
So, see, that's what's been kind of making me wonder too. So you're taking, from all the past ones, you've been taking whatever h has been leading to, and you're plugging that into the very end of the equation, and then that's giving you
Correct.
the last bit of fraction.
Correct, yeah. Yeah, so as h goes to 0, the quantity 9 plus this h is basically going to 9, right? Because we keep adding smaller and smaller numbers to it. Yeah. So yeah, the idea, whether this is an x or an h, in all cases, we're just trying to plug that number in initially. If we end up taking square roots of negative numbers or division by 0, even roots of negative numbers or division by 0, those instances are the ones where we have to start algebraically manipulating stuff. Once we've manipulated it into these types of places, then we're just plugging basically h equals to 0 in for h, or x equals to 1 in for x. So we did see many limits where we just evaluated it directly. Yeah.
So would the whole be at 0 with negative 81?
Right. So this function in terms of h would have a hole at 0, negative 8 over 81. So if you do remember dealing with the difference quotient, you might recognize those last two examples as sort of a byproduct. When it said find the difference quotient of a particular type of function, it's okay if you don't, but typically these showed up, these expressions involving h, those showed up when you were computing a difference quotient. Which again, the difference quotient is no more than what? So that's our difference quotient. What is that? Yeah, so that just gives us an average rate of change. Notice up top we have y values, the difference of y values over the difference in x values. So we don't see that explicitly, but if we write it as f of x plus h minus f of x all over x plus h minus x. Right, that's what we started with. So we just get h in the denominator, but we do have the change in x on the bottom, change in y up top. That's always going to give us a slope, the change in y over the change in x. So our difference quotient is the same thing as the average rate of change, is the same thing as the slope of the secant line. It's just the slope between 2 points. Just curious, who remembers that difference quotient? Who remembers that? All right, so many of you do. The only reason I bring it up is because you might look at limits like that and say, well, like, you know, that's a really weird limit. Why would I ever compute that? Remember our discussion in 2.1. How do I turn the slope of a secant line into the slope of a tangent line? How do I turn the average rate of change into an instantaneous rate of change?
You're going to have h approach 0?
Right, we're gonna involve a limit. That's exactly right. Specifically, if we look at the difference quotient, which was the slope of a secant line, and we allow h to approach 0, what's happening is this location on the x-axis is approaching this location on the x-axis, right? If I let h approach 0, doesn't this x plus h approach x? So in the moment I involve a limit, specifically the limit as h goes to 0 on this thing, the average rate of change now becomes the instantaneous rate of change. Just like in 2.1 where we're looking at average velocities, I think our example was as t approached 1, but that gave us an instantaneous velocity of like 64, I think, something like that, right? So as soon as we attach a limit to our difference quotient, then we get the slope of our tangent line, which is really one of the main ideas of why we're even studying limits. So just for those of you that do recognize this, as we move into chapter 3 and start looking at slopes of tangent lines or instantaneous rates of change, which is our derivative, you'll see that this difference quotient does show up again, and we do have to work with it again because it's in the very nature of how we define a derivative. So maybe we'll just remind ourselves that we'll see this again. in chapter 3. And chapter 3 is all about derivatives. Remember, derivatives was one of the 2 pillars of calculus, so it is a super important concept. And if you remember the difference quotient, remember working with it, it was kind of a pain, wasn't it? Depending on the function, it could be really, really tedious to simplify the difference quotient. But we're going to take simplifying the difference quotient and just tack on the limit as h goes to 0, and that's going to give us our derivative. So if you've seen difference quotient before and you remember it, then you essentially know what a derivative is, or how to find the slope at one point already. All right, questions? All right, we're going to look at a couple more types of functions, like piecewise functions. We're going to also look at one more method to compute limits by hand in this section. So our final method kind of happens when, well, what if we can't simplify it algebraically? What if I can't involve a lowest common denominator? What if I can't rationalize the numerator or denominator? What if conjugation doesn't work? Factoring doesn't work? You know, all of that stuff. So the example that we're going to use to motivate that is x squared cosine of 1 over x. And computing the limit as x goes to 0 on a function like that. I'd say, well, you know, it's cosine of 1 over 0. I can't do that. But there's nothing glaringly obvious to factor out, right? If I factored something out, it's not going to help. Conjugates, et cetera, et cetera. None of those techniques we've looked at earlier will help us simplify, if you will, this function. In fact, the function can't be simplified. So the method that we're going to look at is a method that helps us evaluate, you know, certain types of functions. It's not true for everything, but it is another method. We will actually pause there and come back to this. Before we get into the actual theorem that we're going to use or technique we're going to use to evaluate that, let's just start off with something a little bit more simple, and then we'll apply it to functions. So what if I said, let's say I was thinking of a number. Let's call it capital N for number. So I'm thinking of a number. Let's say where the number I'm thinking about is smaller than or equal to 3. And the number I'm thinking about is larger than or equal to 3. What number am I thinking about? 3, right? Does that seem obvious that I'm thinking about 3? So that's if you understand that, then you understand that theorem that's there below. You understand the squeeze theorem if you understand this. So to sort of extend that into our realm, let's say what if I was talking about a function f of x. So what if f of x had the following criteria? So I know f of x is smaller than or equal to, how does your book write it? Sorry, we could continue this way, but I do want to try to be consistent with how your textbook has this written, so I apologize. Let's call our function g of x. And g of x has the following criteria. G of x is less than or equal to h of x. G of x is larger than or equal to f of x. And this criteria holds for all x, for all values of x. So for any x value, this number, the y value for g is always less than or equal to h. It's always less than or equal, or greater than or equal to f. So the reason the theorem 2.5 is called the squeeze theorem, it's sometimes referred to as the sandwich theorem as well. But basically we're taking this function and we're squeezing it in between two other functions. Now, the reason that helps us is because we're talking about limits. So if I take this statement that holds true for all x, then when I look at the limit, on all of these functions, if I look at the limit as x approaches a, then my inequality is still true, right? Because the inequality was true for any value of x. Doesn't matter what value of x I approach, this statement is still true. Does that make sense? Okay. So the idea is that the two limits on the end, this limit and this limit, we'll just put in parentheses. These are easy to compute. Really, we just mean relative to the function in the middle, it's a lot easier. Those limits are a lot easier than the limit on the function in the middle. So that limit in the middle is the difficult one. Okay. Everybody okay with where we're at right now? If the function g has this property for all x, then we can look at the limit as part of that inequality. And for argument's sake, I guess your book calls it L. So the question is, what if we know the limit as x approaches a on f of x is the same as the limit as x approaches a on h of x, and both of those are the same number we'll call L. Right. So if we know that those two limits on the end are approaching the same number, we're going to call it L. Then what we have is L is less than or equal to the limit as x approaches a on g of x is less than or equal to L. Do y'all agree with that? We just said that they're equal to L, whatever that happens to be. So those limits were easy to compute. We computed them to be some number, capital L. Then what's our conclusion about the limit as x approaches a on g of x? has to equal to L, right? So this number is less than or equal to L, but it's also greater than or equal to L. So this limit, therefore, I'll just say therefore the limit as x approaches A on g of x must also equal L. And that's basically the what the squeeze or sandwich theorem is telling us. So we have f, g, and h satisfying the inequality for all values of x. Remember, except possibly near A, again, that's just the nature of the limit. It doesn't care what's happening at that x value. We just care about what's happening as we get closer and closer to it. And so the limit on f equals the limit on h. That's L, so that means the limit on this difficult function that we've sandwiched in the middle is also equal to L. Does that make sense? Do y'all have any questions on what that theorem is telling us? So what would be the difficult part in using this theorem?
Finding enough f of x and h of x to satisfy that criteria.
Right. So by far the hardest part of using this theorem is establishing an inequality like that. So we're given the limit as x approaches A on g of x. And the difficult part of this, utilizing this theorem, is coming up with these two functions so that g of x is in between those. I will say I'm not going to have you come up with any of these inequalities, but you do need to know how to utilize this theorem. Okay. So with this in mind, we can go back to the x squared cosine of 1 over x function. Are there any questions at all on this? All right. So a couple more minutes. We're not going to finish all of this before we take a break, but let's just at least establish this while it's fresh on our minds. So this is like, if you refer back to that theorem anyways, this is our function g of x. And again, you're not responsible for establishing the inequality. A lot of those inequalities are very, very difficult to establish. So what we need to try to do is try to take x squared cosine of 1 over x and bind it in between two well-behaved or maybe better-behaved functions. So what do we know about the cosine of 1 over x? Do we know anything about cosine of 1 over x?
It fluctuates between 1 and -1.
Right. So remember, the cosine of anything is always in between 1 and -1, right? If I said, what's the cosine of theta in between? You would say 1 and -1, right? So theta, in this case, is just 1 over x. So we know that that cosine of 1 over x is in between 1 and -1. But we're trying to answer the question about the function x squared cosine 1 over x. But at least we have a starting point, right? We've got this as our starting point. What would we do to get the x squared in there?
Multiply everything by x squared?
Right. So if this is always true for any x value, right? X squared multiply by x squared. Now, when would that sort of defeat the purpose if x squared were what?
0.
If x squared were 0, because we would have 0 is less than or equal to 0 is less than or equal to 0, Do we have to worry about x being equal to 0? No, why not? Do what?
It would be defined.
Right, because the limit is, we're computing x is approaching 0, but it's not equal to 0. Okay. So we're going to multiply both sides by x squared. That way we have a negative x squared here is less than or equal to x squared cosine 1 over x is less than or equal to positive x squared. So this is really, put a star there. That's really what we're using to evaluate our limit. Okay, so we've got our x squared and our negative x squared, and then look at its cosine of 1 over x. Remember, we're focusing on the values near the origin for x equals to 0. So when we get, sorry, this was x squared cosine 1 over x. So when we get closer and closer to the origin, we can start to see how that function's bound. See, we're going to get closer and closer. So we've got two nice functions, the quadratics, that are sandwiching in the more difficult function x squared cosine of 1 over x. We'll just take this snapshot and put in our notes. And then we'll take a break and pick back up here. Do y'all have any questions on that? So if this question showed up on the exam, you would already be given what we've starred there. I would say, given this, determine the limit as x approaches 0 on x squared cosine 1 over x.
Does the squeeze theorem only apply to trig functions?
Squeeze theorem does not only apply to trig functions. So if we let's go back to that function, or that theorem rather. So it just says we've got a function f, g, and h, and that inequality is true for all values of x. There is no restriction on those functions at all. But when we do have trig functions, oftentimes this technique is utilized. So we see this more in light of dealing with trig functions and their limits than we do other types of functions, but it is possible to use any type of function in here. Are there any other questions? All right, I'm just going to label this. We can take a break and then finish this after break. So, maybe you can think about now what direction we're going to take and what this limit actually equals to. Okay, so let's take 10 minutes and then we'll continue.
Because it's a So,
Oops, sorry,
I'm just gonna save it. That's the idea from Windows after, it's the same.
All right, so with this inequality established, then what do we know about the limit as x approaches 0 on x squared cosine 1 over x?
It's greater than or equal to the limit as x goes to 0 of negative x squared.
Right.
And greater or less than or equal to the limit as x goes to 0 of x squared.
So if we know the functions bound between those two, x squared and negative x squared, then the limit as x goes to 0 on x squared is less than or equal to our limit, which is less than or equal to the limit as x goes to 0 on positive x squared. Does everybody agree with that? So really, you would be given the inequality, and then to compute the limit, you're thinking about this next step here that we just wrote down. So to compute the limit, we just add the limit to our inequality. What's the limit as x goes to 0 on negative x squared and positive x squared? 0. Right, 0 squared. So now we know this limit of x squared cosine 1 over x is greater than or equal to 0, and it's less than or equal to 0. So what does that limit have to be? The limit has to be 0. All right, therefore, the limit in question is equal to 0. So do y'all have any questions on that, how it works? So in your homework, it'll give you an inequality. It'll say verify the inequality, blah, 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 near x equals to 0. So this is a technology question. It's going to give you, I believe it gives you multiple choices for the inequality. So you just graph the inequality and then choose the appropriate answer. And then once we've had that inequality verified, if this were on the exam, I would just say this is true for all values, and then have you compute what is the limit as x approaches 0 of sine x over x, knowing that this inequality is true. So we start with the inequality. Again, the limit that we're trying to answer is they're stuck in the middle between those two well-behaved functions, 1 minus, or our quadratic, and the function 1, which is our horizontal line at 1. Okay. So we just graph each individual function. To verify that, then that's going to allow us to compute this limit. So based on the inequality, what is our limit equal to? We can't evaluate it directly, notice. There's no way to get that x out of the denominator. So based on the inequality, what is that limit equal to?
1.
Yeah, it's equal to 1. Because we know that now I'm taking the limit as x goes to 0 of that inequality. So function on the left was 1 minus x squared over 6. And that has to be less than or equal to the limit as x goes to 0 on sine x over x, which is less than or equal to the limit x approaches 0 on the function 1. Y'all okay with that? So we just insert the limit into our inequality, compute the limit on the left, because this one is unknown at this point. We don't know that one. X is going to 0, so what does the left-hand limit give us? 1, because as x goes to 0, we have 0 over 6. So that whole thing is 0, which means the limit is 1 minus 0. And so we still have our unknown limit in between. What's the limit as x goes to 0 on 1? 1, right? There is no x there. Another way to think about that as a function of x, this is just the horizontal line. No matter where x is, the y value is always 1. So we've got the limit is in between and including 1, so it has to be 1. in light of the next section especially, this might not have been totally obvious. We might say, well, the top fluctuates in between 1 and -1, specifically at 0, sine of 0 is 0. The denominator is 0. So if we were to evaluate this limit directly, so let's just say direct substitution on this limit gives us 0 over 0. And when we write 0 over 0, let's just make that clear. 0 over 0 means the numerator and denominator are getting closer to or approaching 0. We're not meaning 0 divided by 0. We're just saying the top's getting closer to 0 while the bottom's getting closer to 0. After chapter 2, it's not the last of the limits that we see. So later, chapter 4, 4.7, so really close to the end of chapter 4, we revisit these types of limits that are like 0 over 0 and stuff. So we do come back to limits at a later time. Yeah.
You said we need to know how to graph that?
No, you don't need to graph this, because again, what you would be given, you would already be given that inequality.
Okay.
So we're just verifying the inequality, but let's just say I told you that inequality is true. Then your next step from there to compute that limit is this step right here.
Okay.
So the whole point of this is that we could show that this inequality is true by hand. We don't have to look at a graph. And in fact, the functions that we've seen utilizing the squeeze theorem, they're super difficult. There's probably no way you're going to get an accurate graph. Even if you were to graph them by hand, it'd take at least 10 minutes to graph one of them. So the whole point is to just ignore the fact that we have those graphs. We're just using the graphs to visually show that that inequality is indeed true. But without it, then we're immediately at this step, which leads us to the conclusion that that limit is 1. So yeah, don't worry about graphing these crazy things either. It's just when it asks you to verify, that's how you would verify. One other thing I will add is that we do see specifically this limit again in chapter 3, because this limit is how we, how should I say, this limit is part of how we prove the derivative for sine and cosine functions. So we do end up working with this limit a little bit more in chapter 3, but by then we'll forget about it. Like that'll be a long forgotten thing. But we will see that limit in chapter 3 again as well. That's really all I'm going to say about the squeeze theorem. Does anyone have any questions? The last thing we're going to look at in 2.3 is techniques for computing limits on piecewise defined functions. So we've got the following function, and we're going to compute some of these limits here. So the limit on this function as x approaches 6, what would that equal to? Or how are we computing that?
You use root of x minus 1.
So does everybody agree that we would use the bottom piece to evaluate this limit? Because the bottom piece is valid when we have x values that are larger than 1. So since we're approaching 6, the only piece we can use is the bottom piece. Remember the piecewise functions, the x less than, x greater than, whatever, those second statements are always the domain of the particular piece, but both pieces make up the function. So, if you need to draw a number line to visualize this, that's totally fine. Here's 1, and we want everything larger than 1. So this domain is taking care of all of those x values. So any limit that's completely within that interval, we're always going to use the bottom piece. So if I said, what's the limit as x approaches 1,000, you're going to also use the function root x minus 1. Because 6 is somewhere way over here. I can approach it from both directions because it's completely contained within that particular domain. Our domain for the first piece is everything smaller than or equal to 1. So computing the limit as x approaches 0 on f of x, we would use which piece? The top piece, because again, 0 is totally contained within this interval, and I can approach it from both directions. So limits on piecewise functions, when the value we're approaching of x is totally contained within one of those pieces' domains, is just a straightforward plug that x value in. You just got to know which piece you're plugging into. Is that clear? Do y'all have any questions on that? Okay, so let's evaluate these limits before we move on. The limit as x approaches 6 on the square root of x minus 1 is the square root of 5. Would that be a whole or a point?
Point.
It's a point because the top, or the bottom piece rather, is completely defined when x is 6. How about the limit as x goes to 0 on negative 2x plus 4? That limit is equal to 4. Again, that is a point as well, because it's totally contained in the second piece, or the first piece, the top piece. So looking at the definition of the function, we see that those intervals, or those pieces, are basically broken up by the x value of 1. So in this particular example, any limit can be computed directly except for the limit as x approaches 1, because that's sort of our dividing line for that x value. So as we approach 1, again, maybe visually looking at each domain, one piece includes 1, and we can approach 1 from the left on the top piece. The second piece doesn't include 1, and we can approach 1 from the right. But we can't approach 1 from both directions. So when you're dealing with piecewise functions, these numbers here that show up in each domain, those are the only numbers you have to worry about computing two-sided limits at. Any other number, just plug in. Okay. So we've got two different pieces that's going to affect when we approach it from the left and from the right. So in order to determine if the limit as x approaches 1 does exist, we have to look at the limit on the first piece and the second piece before we conclude anything about this limit. So as we approach 1 from the right on that function, what piece do we use? All right, I heard both.
On the right, you'd use root of x.
Yeah. So we're approaching 1 from the right. So we're approaching 1 through values that are slightly larger than 1. The only way we can do that is on this piece right here. So we have to use the square root of x minus 1 on this as we approach 1 from the right. Are we all clear on that? And that limit would be what?
0.
Square root of 0 is 0. Again, just like the other ones, once we know what piece we're using, just gonna plug 1 into that function. Same thing as we approach 1 from the left, we have to look at which piece can I do that on. It's the top piece. I can only approach 1 from the left, or values that are slightly smaller than 1 on the top piece, which was negative 2x plus 4. As we approach 1 from the left on negative 2x plus 4, what is our limit? Positive 2. Okay, so then what do we know about the two-sided limit? The limit as x approaches 1 on this function? Right, it does not exist. So both of these tell us that the limit as x approaches 1 from both sides does not exist. So this limit, we'll write it here again, this limit doesn't exist. As far as the graph of that, what are our limits telling us about those two pieces?
Jumps at 1.
Right, so those two pieces are not connected. We've got two distinct separate pieces. If those limits were in fact the same, then our two pieces would meet at that particular y value, or at that point 1 comma whatever.
Yeah, can you remind me why does not exist again?
So in order for the two-sided limit to exist, the one-sided limits have to equal the same number.
Is it one of those rules that we did in chapter 2?
Yes. Yeah. So if, let's say part 2 was equal to 0, both one-sided limits are equal to 0, then we would know that this limit were 0. And yeah, that was from 2.2, where we looked at the connection between one-sided and two-sided limits. Any other questions on this example? So, just another example here, and this is here to kind of point out, on this second function f of x, the only time we would need to look at a one-sided limit is if we were asked to compute the limit at -3 or at 2. Because those are the things that show up sort of in each piece's domain. Does that make sense to everyone? Any other limit on this function here can be computed just by plugging in. So if I said, what's the limit as x approaches 0, then we're going to use this function 1 minus x. Another type of instance like this where, we think about the domain of a piecewise function, if I'm approaching it from the left or from the right, could be a function with a restricted domain like the square root of x minus 4, for instance. I guess there's a couple of ways to think about this. We can draw out the number line here. We can think about what does the function root x minus 4 look like. We can just start plugging in numbers. So there's a bunch of ways we can go to look at these limits, but I think maybe visually, hopefully we remember what this transformation is doing. So taking the square root graph and doing what to it?
Shifting it to the right.
So shifting it to the right 4 units. So here we have our translated square root graph, right? So when we look at these limits, one of those limits we can't compute. Which of the limits can we not compute? Yeah, the second one, as we approach 4 from the left, this is our path. We can only approach 4 along this path. We're approaching 4 from the right. If we're approaching 4 from the left, we can see just graphically that doesn't work. There's nothing to approach through. There's no function over there. But if we're approaching, another way to look at it is, if we're approaching 4 from the left, we're approaching through values, I don't know, through values like 3.9, 3.99, etc. And any of those values to the left of 4 plugged in will cause us to take the square root of a negative number. So, you know, graphically we don't need the graph to answer that question. If we think about numerically what we're doing here, and say, well, all of those numbers are going to give me the root of a negative number, right? So just keep in mind there's multiple ways to sort of start thinking about these. If you forget something and you recognize, oh, well, I know what that graph looks like, just draw the graph out and go from there. But in essence, this is, you know, kind of similar to a piecewise function in the sense that we could be approaching stuff that's sort of on the edge of the domain, and we've got to know which side is appropriate to approach through. So are there any questions on what we've done?
That's right above this one. Why is the domain 2?
The domain is actually all of this. So the domain of that function, notice that first piece doesn't include 2, but then the second piece comes in to include 2. So 2 is actually included in this function's domain via that second piece. But the overall domain of this function, here's 2 and negative 3. X is larger than or equal to negative 3 and in between 2. And then the second piece comes in here and includes 2. So really the domain of that function is from negative 3 to 2. Because the domain of this function is the domain of all of its pieces together. Any other questions? So my recommendation is to start 2.3's homework if you can. Hopefully you're keeping up with it. Again, it's totally up to you because it's all due on the day of the exam, but I recommend keeping up with stuff as we finish sections. So we're going to start 2.4. The first page is giving us insight into both sections 2.4 and 2.5 because they are similar in some regards. So in 2.4 we're talking about infinite limits, and in 2.5 we're talking about limits at infinity. So infinite limits versus limits at infinity. The table of values for both hopefully give you an idea of what we're looking at. So in 2.4, what's happening is x, let's say here is x is approaching 0, but as we approach 0 on the function 1 over x squared, the y values keep getting larger and larger and larger. So the limit, remember the L value was contingent upon the y values, depending on what x value we're near. Okay. So as x approaches 0, f of x approaches L. Our limit statement for that, just as a reminder, would look like this. The limit as x approaches 0 on the function 1 over x squared is equal to infinity. So So that is one example of an infinite limit. As a whole, infinite limits don't exist because the nature of a limit is it has to be a finite number. None of these limits actually exist as a limit. It's just we're a bit more descriptive. Instead of saying doesn't exist, we're explicitly describing behavior of the function when we say the limit is equal to infinity. These limits do not exist, even though we write equals to infinity.
So on an exam, when we have an infinite limit, do you want us to note DNE as well as equals infinity? Just
No, so if on an exam, do we want to denote does not exist or infinity? The answer is, in any time you have one of these limits, you always want to designate an infinity or a negative infinity. So for these on the exam, although you are correct if you say that this limit doesn't exist, what we're really looking for is it positive infinity or is it negative infinity? That's what we're looking for. Okay. So what do we have, as far as the function 1 over x squared goes, what does this limit tell us? As I approach 0, the function values just keep getting larger and larger. What does that have to be on the graph of the function?
Vertical asymptote.
It has to be a vertical asymptote. There is no other choice for what could be happening at x equals to 0. If I said, if we know this function 1 over x squared is undefined at x equals to 0, but we were able to simplify it algebraically and get a finite answer like 1 or 5, at that point we know there's a hole. But anytime you have a vertical asymptote, you're always going to have an infinite limit. So in fact, infinite limits are related to vertical asymptotes. And if you think to previous classes on how they were defining a vertical asymptote, we didn't have the language of limits, so we had to say, well, vertical asymptotes are always the 0 of the denominator that are not zeros of the numerator. In other words, factors of the numerator that are, factors of the denominator that are not factors of the numerator correspond to vertical asymptotes. Do y'all remember that? We saw that when you looked at like any rational function. We've seen the process already. How do we know there was a hole in a rational function? Because those factors up top and bottom would divide out. That would give us our hole. The factors that were remaining would tell us where our asymptote is. So like x plus 1 times x minus 1 over x plus 1 times x minus 2. That function just simplifies to x minus 1 over x minus 2. Since this factor cancels out, there's a hole there. We could get an actual limit from that as we approach -1. But what's left over that didn't divide out was x minus 2, so there's a vertical asymptote at x equals to positive 2. Right? Do y'all remember that? So that was our language then. Factors of the, or zeros of the denominator that were not zeros of the numerator. Now here we have a limit way to define what a vertical asymptote is. So this definition is equivalent to this definition. If I compute a limit on a function at a finite number, and it's infinity or negative infinity, that defines a vertical asymptote. So let's write this out. As x approaches a, which is a finite number, and y or f of x approaches either infinity, positive or negative, then the function f of x has a vertical asymptote at x equal to a. And we'll see that it's more, I guess, technically stated in the definition of a vertical asymptote. But hopefully you can see that if that situation arises, no matter what function we're talking about, then there has to be a vertical asymptote there. And so moving forward, that's our definition of a vertical asymptote. How do I know if I have a vertical asymptote? I'm maybe not going to think of it in terms of factors of up top and bottom anymore. I solely want to think about it as if I compute a limit at a finite number and get infinity in return, I automatically know there's an asymptote at that x value I'm approaching. Any questions or comments on this? So shift gears a little bit, just so we can introduce this, and then we'll focus back on limits, infinite limits rather. So in 2.5 we look at limits at infinity. Notice the difference here. Now we have x approaching infinity, and then we're going to see what do the y values do. The previous section 2.4 we're saying, okay, x is approaching a finite number. If the y values approach infinity, we've got a vertical asymptote. Limits at infinity are asking, as x gets larger and larger, what's happening to the y values? So here in 2.5, we're saying as x approaches infinity, and it can be either infinity. As x approaches infinity, what does f of x do? What does f of x do? That's really the nature of limits at infinity. You've studied this concept too with polynomials and with rational functions. Specifically, I think are the only ones you've ever looked at prior to this course. But for any function, if we're questioning what do the y values do as x approaches infinity or negative infinity, what is that concept related to functions? Do what?
It relates to horizontal asymptote?
Okay, so particularly with rational functions, it relates to horizontal asymptotes, right? What's happening way out here to the y values and what's happening way out here to the y values. Do y'all remember that? Like so just draw some rational function that you might have seen in the past. If I drew that out like that and said there's a horizontal asymptote at 0, talking about way out here, as x approaches infinity, what do my y values do? As x approaches negative infinity, what do my y values do?
0.
Yeah, they're approaching 0, right? Same idea with 1 over x squared. As x gets closer and closer to infinity, or larger and larger, what are my y values doing? They're getting closer and closer to 0. So what that means is, way out here on this end, that my function is leveling off towards 0. It's flattening out. It's a horizontal asymptote. Do you remember that? So we won't say specifically that limits at infinity describe horizontal asymptotes, because there are other types of functions that up to this point we haven't seen yet. In general, we're just saying at this end, what's the function doing, and at this end, what's the function doing. So these types of limits are just describing a function's end behavior. Okay. So let's state that. These limits if they exist, describe a function's end behavior. Lumped into the classification or the concept of end behavior is that of a horizontal asymptote. But some functions don't, like this function we drew on the board, in either direction it flattens out to 0. Some functions don't do that. So within this, horizontal asymptotes are included. Typically, we've seen functions, mostly functions that have one single horizontal asymptote, but there are functions that have 2 horizontal asymptotes. So the more technical way is the end behavior, horizontal asymptotes, if those limits exist. It's kind of the same thing, but since we're computing limits out here and out here on the end of our graph, let's just think about that more generally as an end behavior. On the ends, what does the function do? And we alluded to this last class, I believe. An example of a function that has 2 horizontal asymptotes is the inverse tangent, or sometimes you might see that as arctangent. So it looks something similar to that, where we have pi over 2 and negative pi over 2. So specifically here, if we said as x gets closer and closer to infinity, my y values get closer and closer to pi over 2. So the limit as x approaches infinity on inverse tangent is pi over 2. Also, the limit as x approaches negative infinity on the inverse tangent is negative pi over 2. So we wouldn't just say there's a horizontal asymptote of pi over 2. Here, we say the end behavior on the positive end is approaching pi over 2. On the negative end is approaching negative pi over 2. Could we have more, any function, no matter how elaborate it is, could any function have more than 2 horizontal asymptotes? No, why not?
Because if you have two y values for an x value, it's not a real function.
You're right. So two y values for a given x, you don't have a function. It's no longer a function. But also we see that explicitly because the end behavior describes all horizontal asymptotes. There's only 2 ends to a graph, right? Positive infinity and negative infinity. So at most, you can have two horizontal asymptotes for any kind of function. Because you've got behavior out towards infinity and behavior out towards negative infinity. There's only two outcomes. You have seen in the sense of rational functions, they always had only one horizontal asymptote. So remember that. Rational functions always have at most one horizontal asymptote, but other functions in general can have up to two horizontal asymptotes. Rational functions have at most one horizontal asymptote. I'll keep solidifying this because it does get a little bit tedious. So what does that mean? In the sense of a limit, as long as we're talking about a rational function, the limit as x approaches infinity, we'll call it capital R of x for rational function, equals the limit as x approaches negative infinity. If there is an actual horizontal asymptote. So think about all the rational functions you ever graphed that had a horizontal asymptote. It always approached the same value. Whatever that value is, I don't know. Let's just call it L. So, can we combine the two? Is there ever an instance where the limit as x approaches infinity on some function is also equal to infinity or negative infinity? Is there ever an instance that we can think of?
Linear functions.
Yeah, like a linear function, right? On a linear function, as x approaches infinity, so do the y values. Any other kinds? Linear. Polynomials, right? Quadratics, cubics, all of those. Quadratics, cubic, any polynomial. Which of course a linear function is a polynomial, so as x gets larger and larger, y could get larger and larger, specifically if we're talking about polynomial functions. So yeah, we have a limit or an end behavior that doesn't exist because the function, any polynomial just keeps growing and growing and never flattens off. Can you think of a function whose end behavior is both? Like a function that does have a horizontal asymptote and it also goes towards infinity?
Square root function?
So the square root function doesn't ever actually level off. The square root function just gradually keeps growing and growing.
I meant as a sort of like it can't go below zero.
So it can't go below 0, that's totally correct. But when we're thinking about a horizontal asymptote, the function is getting closer and closer to it as we proceed on. You know it, you just maybe, it's not totally fresh. Maybe you're not quite sure what I'm asking. What about a function like this?
Cubed root.
Not cube root. Here that point's 0, 1. Okay, yeah, not log, but the latter, the e to the x, right? This could be e to the x. Any exponential function, a to the x. Notice we have different end behaviors for that, because as x goes towards positive infinity, the function values get larger and larger. But as x goes towards negative infinity, the function values flatten off to 0. So it's cool if you didn't remember that, none of that, because once we compute a limit at infinity, it's going to tell us all of this information. We don't really have to remember all of this. Do you remember the scenario where we're talking about a rational function? You had to look at the degree of the numerator and the degree of the denominator and say, okay, well, is the degree of the numerator larger than the degree of the denominator? If so, then there's a horizontal asymptote here. Is the degree of the denominator larger than the degree of the numerator? If so, then there's a horizontal asymptote here, right? You remember all of that stuff you had to remember for horizontal asymptotes? It was kind of a pain. You can forget that stuff now, because when we utilize a limit, it's going to tell us that information. We don't have to remember all of those criteria for a horizontal asymptote. All we've got to do is know how to compute a limit as x approaches infinity. That's going to tell us everything we need to know. All right. Sorry if that seemed long-winded. I really do want to tie this stuff into things maybe you forgot, but you should know. So I'm just trying to tie all these concepts into things that you've already learned, so when you see them, you can kind of, just tilt your head a little bit and get the basic idea, because you have experienced it before. All right, but right now I want you to take away that in 2.5, limits at infinity describe end behavior, infinite limits describe vertical asymptotes. That's a nutshell version of what we were trying to say there. Okay. Do y'all have any questions? We're going to compute these limits, all of them by hand. So that's where we'll start on Thursday, is computing these things by hand. See y'all Thursday.